Hi, everybody. Welcome back to the Optical Science Colloquium. It's again like a pleasure to see so many of you here today. Today we're going to have Michael Gehm. Michael is a professor in ECE and physics at Duke University. He's actually a person who is very well known in Arizona because he was a faculty in ECE for 6 years, right, before he moved to Duke. And I should say that he also got his PhD from Duke as well. Michael is interested in computational imaging and sensing, imaging through turbid media, X-ray imaging, and fundamental physical optics. He also, of course, won many prizes. For example, he is a fellow of SBIE and Optica. And Michael, I keep it short today. We are actually very excited to have you here today, and we are very looking forward to your talk about one-way smokes.
All right. Yeah. Thank you, Florian. Yeah. Thank you, everyone. It's a pleasure to talk to you today. So thank you so much for the invitation. So as Florian said, my talk today is toward one-way smoke and engineering asymmetric vision in a reciprocal aerosol environment. Before I get started, I just want to sort of set the stage. This has probably been the most unusual project, not technically, but most unusual project that I've worked on as a PI, as a faculty member. It's, as you can see from the acknowledgement, it's funded by DARPA. It was motivated by a question that was asked by DARPA. For those of you who know DARPA, there's the Defense Sciences Office, which is generally a very fundamental organization. And I've never been involved in a project out of that organization that was as focused on specific high-level goals as this one was, nor have I ever had one that had a classification guide. And so that meant two things. Number one, I had to make this and put this together almost 2 months ago. So it doesn't have the most immediate results. I will try to talk about where, to the best I can where we are, but there's also a couple things that I can't share and that I can't talk about. And so I apologize for not being able to do that in some places. Okay, so I'm going to talk a little bit, this is the outline for the talk, a little bit of motivation and introduction, the goal and why we think this goal might have any hope of succeeding. As was mentioned in the abstract, when you start talking about the possibility of making an asymmetric vision environment where one person can see better than the other, a natural question is, what about reciprocity? So we'll talk about that. And then there will be a number of different approaches that we've identified and started to explore and develop tools around that sort of emerge from our thinking about reciprocity and thinking about these different ways of creating vision asymmetry. And then I'll say a little bit about what's next. All right, so setting the stage, motivation and intro. The request, the inspiration, the ask that or the specific goal that came from DARPA was to try and create an aerosol that would have the ability to create an asymmetric vision environment. And by that, I simply mean better ability to see in one direction than in the other. Jokingly, everybody immediately started referring to it as one-way smoke. And there are some constraints on the approach and the performance metric that I'll get to after we get through some of this provisional stuff and preliminary stuff. But the basic idea is that we want to be able to have something out in the environment where one side can see through it much better than the other side can see through in the opposite direction. That's the basic idea. So why do we even think this is plausible? What was the initial motivation for even asking us to think about this problem? Well, it turns out that there is a patent from 1997 entitled Method for Creating a One-Way Visible Screening Smoke. And the author is a U.S. government scientist who focused on obscurance, the development of smoke screens and other types of items that you would disperse out in the environment to try and impede vision. And the patent provides absolutely no details. It has no theory. It discusses no experiments. It discusses no specifics. The only statement is that the result can be understood in terms of varying contrast available and the impact of glare. So that'll become important in a minute. There are, though, even with no other details, there are some mentions of specific sizes of particles and instantiations that suggest that this had been experimentally validated or explored at this government lab. Okay, so that was where things stood in 1997. It went completely unnoticed by the vast majority of the community. But in 2014, academics discovered the patent and they developed a theory around it, and they actually validated it with experiment. We're going to come back. You don't need to dive into this, but it was one-way visibility using two parallel aerosol clouds. So it was one cloud, which was primarily scattering in nature, one cloud, which was primarily absorbing in nature. And they published the results in open literature. They had experiment that it's, not a dramatic difference, but a very clear difference in sort of the ability to see the checkerboard target in opposite directions through these two parallel plumes. And so this rediscovery is what then prompted the question that ultimately led to DARPA asking, could similar effects be achieved in a single plume with modern materials and, interestingly, active control? What if you had the ability to do something to the aerosol to give you an additional degree of freedom? So then the natural question, again, my very first question was, wow, that seems weird. What about reciprocity? So just a reminder for everybody, there's a lot of reciprocity theorems in physics and in electromagnetics. The one I'm talking about is the Helmholtz reciprocity, which states that a ray and its reverse undergo equivalent attenuation. And that's sort of from a transmission viewpoint. If you want to talk about interaction with a surface, then this becomes a formal statement about symmetries of the BRDF. Now, colloquially, Helmholtz reciprocity is often stated as, if I can see you, you can see me. And I want to point out that that's not a formal scientific statement. And that there are words in there like see that are doing an awful lot. And so that's sort of the motivating point here, is that this is how a lot of us intuitively think about reciprocity, but of course, this is not the statement of reciprocity, right? We can have formal versions of this. And to point it out, we all know systems, everyday things, where we might say there is an asymmetric vision environment. The thing that inspired this to be called one-way smoke, a one-way mirror, in certain situations, you have a much better vision process through in one direction than in the other. We've all had the experience of being very close to a fine piece of mesh or a fine fabric, and you can see through it and see people on the other side just fine, but they can't see you if they are at a different standoff distance. There's a thing called the shower curtain effect, or we can think about items with power, right? And so the vision, the quality of the vision, what it means to see is different through these things, and that's not a statement about rays, right? That's not fun. Like imaging and seeing is about more than a ray and its reverse. And that's sort of like the deeper philosophical statement I want to make, and the deeper philosophical realization that we had as we started thinking about this problem. And so it turns out that there are a number of aspects, I'm going to talk to you about several of them, of Helmholtz reciprocity that make it not exactly the thing that you need to bring to bear to understand this idea of image asymmetry. So there are a number of different approaches that we sort of developed over the course of looking at this, and then we started to build analysis tools and in some cases some experimental probing to help us better understand this. So the first that I want to talk about is glare. So remember, that was mentioned in that 97 patent. So I guess the statement I would make is that reciprocity is a two-player game, right? So the statement is that these two rays that are reversed have the same overall attenuation. As they used to say in the old video games, player 3 has entered the game, okay? So when you have multiple pairwise reciprocal relationships, the total amount of light going in this direction and the total amount of light going in this direction do not have to be the same thing, right? They don't have to be the same quantity. It's true that the light emitted from player 2 is attenuated as it goes to player one by the same amount that the light emitted from player one is attenuated as it goes to player two. But the total amount entering the imaging system, the eyeball, the camera, the whatever here, does not have to be the same as there because of this breaking or this entry of a third party. All right. So all of the individual pairwise pieces are still reciprocal, but it no longer becomes the totality is no longer necessarily a symmetric quantity. And this is fundamentally the idea behind that 97 patent and the 2014 paper. So here's the theory. So we first of all, this paper that's expounded on the 97 patent, 4 authors. I'm going to refer to it as the ABGJ paper after their initials. It's essentially a radiometric argument. They're not saying anything deeper than the idea of you have these 2 plumes. You have one that is primarily scattering. They approximate it as completely scattering. One that is predominantly absorbing. They approximate it as completely absorbing. And you have an object and a background brightness on the left, and you have an object and a background brightness on the right. And they each send those brightnesses through the plumes where they get affected by the transmissivities of the plumes. And so we have transmissivity of the absorbing plume as we go this way, right? There's what we started with, that background brightness. We go through this plume. It's now the background brightness times the transmissivity of the absorbing plume. And so they just do that. And then they say, okay, and then the interferent, they consider the sun, into the scattering cloud is going to produce light coming out on that optical path. And they state what that brightness is. There's going to be some brightness going in each direction. Again, assume it to be equal. And then they look at the impact of all of that. And so they compute the contrast ratio of what can be seen on each side. And the contrast ratio is just the difference in the brightness of the object in the background divided by the background plus the glare is basically the way that it works out. And they compute that in each direction in this overall ratio of the, so then they do a ratio of those contrast ratios. So this is the contrast ratio is seen on the absorbing side. This is the contrast ratio seen on the scattering side. And then they factor things out where this is the original contrast ratios of the object and background here and object and background here. They allow the fact that the 2 sides may not have been presenting equivalently contrast valued images to the other, and that initial asymmetry is captured here. But then this is then the impact of this interferent scattering that's put onto the optical path, the glare, as well as the impact of the transmissivities of the plume. So they work that out. And in fact, they then show in their experiment in that 2014 paper that they get relatively good agreement to this very simple radiometric style theory. But one of the first things as we were starting to ramp up and learn about this aspect of vision asymmetry is that there's a number of limitations to this approach, right? So first of all, they are manifestly saying one plume is purely absorbing, one plume is purely scattering. There's no real nature of scattering things that are true mixtures of the two. The transmissivities, these TS and TAs, they're just empirically set. They're just numbers that are just said, oh, well, the transmissivity of this plume is this. It's not connected to the plume, to the scattering and absorption details of the aerosol at all. I'm going to say that it only treats the interferent at the zenith. Effectively, there's no because the intensity of the glare is just a free parameter. Notice it's not connected to anything. It's not connected to the brightness of the interferent. It's not connected to the parameters of the plume or anything. Then it's certainly not sensitive to where the interferent is relative to stuff. So, you know, it's just this generic number that's just put in. And so again, as we were ramping up, one of the first things we said is, well, we feel like we can do a better job than that. So this is not rendering super well. Sorry for the low res. But basically, we've parameterize the plumes now by albedo and extinction coefficient and the dimensions. So we now have physical parameters for the plumes. Again, they're still rectangular prism. Like we're not, you know, at the level of arbitrary shapes of plumes or anything like that, but we can at least affect the scattering and the extinction and the absorption properties of the plumes independently. We allow the interferent to exist at an arbitrary angle now. It doesn't have to just live at the zenith. And these path transmissivities are now result from these plume parameters. Again, the setup is the same. There's an object brightness, a background brightness, but everything is now actually physical in some basic sense. Now, how we deal with, so the direct paths are relatively straightforward, right? They're basically going straight through these plumes. We know the albedo, we know the extinction, all that. We know the dimensions of the plumes. So figuring out what happens to these straight through paths, these direct paths, that's what the subscript D is meant to represent, is relatively straightforward. And then what we did for the indirect paths for when we have brightness coming from the interferent and some of it being redirected onto the imaging axis, onto the imaging path, is we borrowed some path integral solutions to radiative transport that had been formalized in biomedical optics and tissue optics to describe the scattering in these things. And we were able to use that to help us connect the plume parameters and the interferent brightness into what emerges from the sides of the plume. We structure things exactly like like the prior paper. We have sort of the bare contrast ratios, so we're not restricted to having scenes on each side that are symmetric. There can be a built-in asymmetry from the scenes, but the piece we actually care about is this other factor that we call the asymmetry factor, and it has, you know, a lot in common with the prior version. But again, these transmissivities are now all directly computable from the plume parameters, and this has now been submitted to applied optics. This is a true generalization. We can show that in the limit that we make certain assumptions, we extract exactly their earlier theory from it. What's one of the things that's interesting is this off-zenith interferent. There's an asymmetry in the deflection angle, right? For this, if the interferent is up here angularly off to the left, let's say, then it has to deflect by much less of an angle to come out this way than it does to redirect through multiple scattering and come out this way. And so you can lead to a big imbalance in glare depending on this angle, right? And so the well-known idea that you probably want to have the sun at your back, that's a good thing to have, emerges naturally from this thing. And for certain reasonable assumptions, we can even have an analytical solution to the path integral solution, which means we can also very easily then optimize this theory for over variables of interest. So if, for example, we want to hold certain things constant, we can say, oh, well, then the plume should be this tall if you want to maximize the asymmetry, or if you know, so we can hold whatever we want fixed in the theory, and we can optimize other parameters, you know, albedo of the particle or something like that. So that was neat, but not really the main solution that we were proposing to the thing that we were asked to do. Remember, we were asked whether or not we could have a single plume approach to vision asymmetry with when given the ability for active control. So obviously that was still a two plume solution. We were getting our feet wet. We were learning about what people had done before and trying to address some of the shortcomings that we had identified in that. But our main approach that we had originally said, we think this is the way to go after it, is with oriented asymmetric particles. And so again, now getting a little more specific into what the ask was. So the request was to develop a specific particle design and design approach, if you will, and overall system approach to make a single plume obscurant that gives you this vision asymmetry. We were allowed to give ourselves the degree of freedom of being able to actively address something about the plume. And again, like I said, this is for a DSO project. This got really way down in the weeds. There was a specific performance metric that was our only thing we were supposed to care about, which was the identification probability, PID, in one direction relative to the detection probability, PD, in the other, and is specifically evaluated at the point where PD is 0.5. So it went when you've got this obscurant in between, when somebody looking that way can detect something that is there 50% of the time. The question we were needing to understand to optimize was, what's the probability that they can not only detect, but identify what's on this side? So again, very down in the weeds. No reason to believe that that's a particularly good metric, but it is what was, it was what was handed out at the very beginning. The whole idea was that this whole performance would be evaluated through a US government software tool called NVIPM, the Night Vision Integrated Performance Model, which calculates these kinds of expected probability of identification and probability of detection. And boy, it would be great if somebody breathing these things didn't die. So the request was, could it please be non-toxic? Because the normal obscurants that are in use tend to be a lot of metal flakes, metal wires, and they don't always behave super well when they get lodged in the airways. Ultimately, the goal was to have simulation backed by some experiment, and then potentially later on that would scale up to test in a 1 meter cubed, and then eventually that would scale up to room scale testing in a 75 cubic meter room. So, you know, think basically a 5 meter by 5 meter by 3 meter tall. So, you know, not so much smaller than this room. And as I mentioned, classification guide covering probability of identification and probability of detection performance. So the results of those numbers covered, as well as experimental data if the particles had sufficiently large mass extinction. So if you had sufficiently, if for a given gram of the particle, if it had a sufficiently large enough extinction of light, extinction coefficient, then that data then became controlled, as well as any of the advanced synthesis methods. Okay, so this was the ask. All right, so we saw that glare is a two-player game. That was one way in which the colloquial understanding of reciprocity didn't necessarily map over. Another way in which it doesn't map over is that reciprocity is about total attenuation. So in an aerosol, total attenuation is described by extinction, which is absorption plus scatter. So reciprocity is talking about equivalency of extinction in the two directions, not about equivalency of absorption and scatter. And so you could have mismatched absorption and scatter in the two directions, provided they were mismatched in a way that their sum was constant. Okay, so you could have a higher scatter direction and a higher absorption direction. And so why do we think that was plausible? Well, in 2014, Andrea Alou actually explored this absorption scatter asymmetry in a nanoparticle dimer. So looked at 2 gold nanoparticles and identified that when you added attenuation, when you added absorption, when you considered absorption, then extinction still maintained reciprocity, but you started to get higher scattering in one direction and higher absorption in the opposing direction. So this seemed like a plausible approach, or a plausible thing to consider. So what we said was, we're going to consider a particle geometry that has a highly scattering piece and a highly absorbing piece in close proximity, essentially fused together on the scale of about a wavelength. And that we would try to align and orient these particles at a standoff distance using acoustic fields, that we would use applied ultrasound fields to make these particles all point in the same direction. Now, align I'm using to mean parallel axes, and orient means same direction on that axis. So we could be aligned, but have the highly scattering ends in random mismatched directions, but oriented, they're all pointing in the same direction. And so if you had an aligned and oriented plume, and we believe that it's possible to have higher scattering in one direction across a particle and higher absorption across the particle in the opposite direction, then maybe that has interesting impacts for imaging, because we would imagine that the scattering is going to scramble image information, whereas absorption is just going to attenuate it. And so there might be a sweet spot where in one direction, yes, you've lost more stuff through absorption, and that light, those photons are gone, but what you have and what you do receive still contains the interesting information that tells you image. It provides image information to you, while in the other direction isn't attenuate or isn't absorbed as much, but is scattered and scrambled in a way that becomes impossible to or highly difficult to undo. Now, we were targeting particles of size 10 microns for a couple reasons. Number one, we have to worry about the settling time in air. So this is not going to be a useful obscurant if it falls to the ground in a fraction of a second. 10 microns gives you minutes generally of settling time. It's also the size that is preferentially embedded in the upper respiratory tract, where they tend to be expelled, as opposed to the lower respiratory tract. And we were going to try to use biocompatible materials if possible. And I'll say more about that in a minute. And then we were going to try and do this in the midwave. So this last part was our attempt to at least try to move towards less toxic particles. And then again, midwave for a variety of reasons that I'll talk about later. All right, so now here's where I have to talk about the other. It was a big team effort. So with me at Duke, it was Professor Stephen Kummer, who among a variety of things he's expert in, is also in acoustic metamaterials and acoustic control. So he was focusing on the acoustic pieces that I'm going to be telling you about today. And Ben Wiley is a professor of chemistry who is expert in particle synthesis, and especially high rate, very simple synthesis methods. In addition, we were teamed with small company Signature Research with the technical team members, Amalia Anderson and Ben Hendrickson, and their focus was on calculating things like plume MTF and doing this performance metric evaluation. So basically anything that conceivably crossed into that controlled region lived here and did not cross the blood-brain barrier to the university side of things. So the notional particle we decided we wanted to look at was a copper nanowire whisker growing from a copper oxide octahedron. So the interesting thing about this is, number one, just going back to that toxicity, copper is actually absorbed pretty well by the human body, so it's less toxic than some other metals. It also exists, this particle shape, this micro club, exists at the Venn diagram sort of intersection of things we might expect to have this asymmetric behavior. Notice we have a dielectric, this copper 1 oxide octahedron, which we might expect to be pretty strongly scattering. And then we have this copper nanowire, which we might expect to be at least some level of attenuating. It's also long and rod-like, so this is the kind of structure shape that we might expect to need if we're going to acoustically align it. And it was the thing that was in Ben's wheelhouse to be able to fabricate in large volumes, relatively large volumes, with very little process development. And I'll say more about that in a minute. But further, things like the length of the wire or the size of the octahedron were tunable through some changes in the chemical process. So we had some reasonable tunability of these parameters if we wanted to try and optimize the details. Now you can see we certainly don't get perfectly repeatable microclubs with this thing. But these are very early micrographs. They got more uniform, and we started looking at like filtration and purification techniques. But it's relatively easy to make very large quantities of these in a relatively straightforward way. Then we started looking at simulation using COMSOL and CST, so full wave simulation of these microclub structures, to understand what the far field result looks like. Now, I should go ahead and tell you, we should talk a little bit about how we're going to look at plots like this. So the way they set things up is 90 degrees represents propagating along the axis of the microclub. And what you see here, so this is going to be the rotation of the microclub relative to the incoming illumination, and then you're seeing something related to the far field pattern. It's actually the mass coefficient as a function of this rotation relative to the incoming illumination. Now, there's you'll notice this only goes over 180 degrees because the solid line is one orientation of the particle, and then the dashed line is it has been flipped. Okay, so these both represent, so 90 represents end on in the two different orientations, and then we get the different rotations relative to that. And the thing that I want to point out is that the green is the extinction cross-section, and you see that the dashed and the solid lines are on top of each other because the particle is reciprocal. But if we look at red is the scattering cross-section, and blue is the absorption cross-section, you can see that there are places, including especially on axis, regardless of whether we're looking at copolarized or cross-polarized light, where we get significant deviation in the individual absorption and scatter behavior in the two different opposing directions of the club. So we do expect from these full wave simulations that we would see this asymmetric scattering and absorption behavior. This is a particular simulation. You can see this is, the cone or the wire is about 5 microns. The octahedron is about 2 microns on a side, and the wire itself is very slender at 1 micron. Yeah. Yeah, so what I mean is, so blue is the absorption cross section. So the absorption cross section's mass coefficient. So it's the amount of absorption cross section per gram, okay, of material. And we put it on the mass. So again, all of these are cross sections. So extinction cross section, scatter cross section, absorption cross-section, and we were always very conscious of going ahead and backing this out to the mass version of that based on the particular particle size we were simulating, because of the fact that once we got over a certain amount, the results, if we did an experiment, would be controlled. So we always wanted to work in these mass units so that we made sure that we weren't going to set ourselves up for problems if we went into the lab and made a measurement. Okay, so that was the basic particle, and we'll talk about synthesis of it in a minute. But now this is me, an optics person, talking about acoustics. So I'm trying to present my colleagues' insights. But we can think very simply about the acoustic force and torque on a small particle. And so you can do a perturbation theory analysis of what happens as you have an oblate, or ultimately we're going to work with rod-like, but the results work out to be the same. Particle under some propagating sound. There's a stable equilibrium when the particle is broadside to the incoming wave. So you've all probably, if you can think back to having seen a twig on a pond or something, and the twig likes to align itself broadside with any ripples, right? It aligns to the way crests and troughs. Okay, and so that's the stable equilibrium in the acoustic field, and there's a torque, and for a wide degree of initial angles around that point, you get a nice linear restoring force. And so, you get this natural, the acoustic field naturally wants to rotate the particle into this alignment that is broadside. They spent a lot of time trying to make sure that they understood how to simulate this because we were ultimately moving to more complicated particle shapes. So did they have some faith in their simulation? And so indeed they were able to get pretty good agreement between theory and simulation on the acoustic torque of some things. And then some of the interesting results is it doesn't matter whether it's a standing wave or a propagating wave. And that's great because obviously the real world application would be essentially a free wave, right? We wouldn't expect, it's open air. We wouldn't expect any reflected waves coming back to give us a standing wave. But obviously working in the lab environment, it becomes very challenging to avoid standing waves. We have to do a lot of engineering of the chambers and stuff to try and avoid that. But we can see that in terms of the torque, at least, it doesn't matter. Okay, there are other issues that happen when we have acoustic standing waves, but at least in terms of the manipulation of the particle and the alignment of the particle, it doesn't matter if at least for the frequencies of interest, it doesn't matter. Okay, so that gave us some again gave the acoustics team confidence that they could apply these tools in more complicated scenarios. Then the other question is, can we go ahead and get this torque without just pushing the particles, right? We don't want to make a wind that blows this stuff away. We just want to rotate what's in it. And indeed, it turns out that to very good approximation, first of all, the torque is independent of the frequency of the wave, as long as the particle is deeply sub-wavelength. And it turns out that for a propagating wave, there's actually no net translational force. There's only torque. And so basically, we can work with low frequency ultrasound, which has a number of benefits. Number one, we can have relatively long propagation distances. It doesn't attenuate super fast in air, so we can achieve useful acoustic power densities at tens, maybe hundreds of meters using available transducers. And let's see, yep, and we don't blow the cloud away, which seems like a good thing. But we don't want to have to do that out in the open as we're trying to learn about this some more. So they also looked at whether or not they could look at particles in water at a different frequency as an analog for the particles in air, right? Because again, you have to get them suspended. You only have a certain amount of time to suspend them, and those time scales before settling are much longer or even infinite, potentially in fluids. And it turns out the nice thing is that the dynamic equation is the same whether or not you're in a fluid that's air or in a fluid that's water. And so now this is for not the micro club, but for 100 by 7 micron carbon fiber. Again, I said that the particles for the acoustic stuff needed to be deeply sub-wavelength. The wavelengths we're looking at are in the order of 2.5 centimeters. So anything, even whether that's the 10 micron micro club or this 100 micron carbon fiber chunk, they're all deeply sub-wavelength. So they're all having these nice behaviors. And it turns out that you do have to up the intensity to get the same time scale in water than in air, but it turns out that that's essentially the same ratio that exists in the available power in commercially available transducers. So it's just as easy to achieve that power density in a liquid than it is to achieve the other intensity in air. So looks like water was going to work as a good analog. And then I mentioned synthesis. So this is now from Ben's group. He developed an entirely what he calls a one-pot synthesis method. Basically, again, I'm not a chemist, but he's got this sodium hydroxide. He has some copper something or other. I'm not sure what is that, nitrate. I'm not sure, and some EDA, and basically adding a couple additional reagents and some time, and basically the microclubs just grow, and they just you get the octahedron that's a dielectric, and you get the nanowire that's the conductor. And again, by tuning some of these concentrations and tuning these time steps, you can make some tuning adjustments to the particle geometry. And then he proceeded to scale that up to the point where he was working with 10 liters of the material at a time. So there would be big shipments from Amazon of the different reagents, and they could generate in one batch about 2 grams. And again, these are relatively small particles, so that's a lot of particles, 2 grams of microclubs in a single 10-liter batch. And then he had a spray dryer, which could take the microclubs in solution and reduce them to just powdered, dried microclubs that were available. All right, and then so that's the basic idea of the torque and the synthesis. We have to think about how we would design the particle, but also we need to be able to analyze it. So this is work that's then done on the other side of that blood-brain barrier at Signature Research. So they had some of their custom tool chains that they already had, because they do a lot of work in mid-wave system analysis, where they could do Monte Carlo ray tracing of basically a slant edge, a mid-wave slant edge. So 2 different temperature objects with an edge. And by doing Monte Carlo simulation of a plume and without a plume, they could extract out the MTF that the plume was inducing. Okay, and then that plume was the input that went into that government tool that could then predict the various metrics, the probability of identification, probability of detection. So that was sort of the piece that lived on their side. So the overall analysis flow was that we had particle parameters and we had a full wave solver, which we could use to predict the phase function and cross sections and other aspects of the scattering and absorption of the plume particle. Those particle factors went to Signature into their rendering engine and their sensor effects. They would simulate the slant edge image. They would get the MTF that would go into NVIPM, and then they would get these PD and PID performance metrics. And then the hope and the thought was that then we would go back from here, and that would feed back, and then we would optimize and iterate on the particle geometry. Now, one of the things we immediately learned, not surprisingly, we knew that the full wave simulation was extremely computationally expensive. Also, the rendering in the Monte Carlo was also computationally expensive to get a sufficiently high quality MTF estimation. So then we started looking at whether or not we could have an ad hoc metric based on just these phase functions and other cross sections and other particle parameters that might allow us to close this loop and start to do some optimization stages before we went across to this side of the boundary. And then the other thing that we were hoping was that eventually we might be able to come up with some analytic ways to get non-rendering based MTF estimates on the university side of things. And so we started working to develop analytical tools that lived on that side of things. Now, the microclub we could parameterize based on sort of the different geometric parameters that Ben said he thought he could achieve using tunings of those reaction parameters. And so we ended up with 4 geometric configuration parameters, and then 1 parameter that was frequency or wavelength, whatever you want, because we said we wanted to be mid-wave, but we didn't say exactly where we wanted to live. And again, because the materials are their properties are frequency dependent, that frequency change doesn't just map onto the scale change of the particle, right? So it really is an additional freedom. And then we could start doing Bayesian optimization of these parameters. And so we could wrap basically a Bayesian optimization loop around the full wave solvers, and we could choose different. Again, this is at the stage of ad hoc metrics. So we can say, well, we think we want to maximize the difference in the forward absorption cross-section and the backwards scattering cross-section, right? We want to make the two directions as asymmetric. We want to create as big an asymmetry in scatter and absorption as possible. That seems like a not crazy ad hoc metric to choose. And so then we can trace different things. So this is the absorption mass coefficient. This is the scattering mass coefficient in the two different directions. And we can let the Bayesian optimizer go, and it's playing with all these parameters. It's adjusting the octahedron. It's adjusting the wire size. And you can see that we end up with with higher backward absorption than forward absorption, and we end up with higher forward scattering and lower backward scattering. So, and again, their difference is exactly opposite, right? So we are maintaining this extinction reciprocity is being maintained automatically because there's nothing non-reciprocal about the particle. And these are the different some of the different geometric parameters. You can just see it kind of working in, and as it's optimizing sort of this total loss function that exists up here. And again, totally ad hoc. So the whole point is we can do this, and we think it's not a unreasonable metric to use, hope it's pushing us in a good direction, but stressing there's no direct connection to imaging performance at this point. This is just an ad hoc choice of what we think might be a good thing to maximize. So then trying to work towards some of this non-rendering MTF estimation, we started working to develop a transmission matrix approach to how imaging might work in these aligned plumes. And so just to stress, this is one of the places, again, most unique experience of my research career, in that very specific goals. And as we started tackling them, we realized they had been built with an assumption that sort of the base theory was all done. And sort of everywhere we looked in the optics and in the acoustics, there were so many places where it seemed like there were huge areas that were still open questions. So we found very little literature on just radiative transport and propagation in an aligned plume. In general, in aerosol analysis, the assumption is that the particles are randomly oriented, and there's all these places where that's averaged over. That if we have the ability to orient and align these particles, that's no longer the case. And so let alone imaging through them, right? Just propagate. How does propagation of light work? So we started working with a transmission matrix approach that I was familiar with from things that are used in like memory effect imaging and other scatter related scenarios. And the goal was to try and get some kind of predictive capability, starting with just basic radiometric sorts of insights, maybe progressing to imaging and maybe MTF or something like that. And then hopefully a framework that we could also start to think about, well, what happens if the plume isn't completely ordered, right? It's not going to be perfectly aligned, or the particles aren't going to be completely homogeneous. So how do we start having a framework where we can fold in ensemble averages of some of those inhomogeneities? So the very straightforward approach, again, this transmission matrix approach, is the idea that if we have an input vector that is the angular power distribution that's going into the plume, and there's obviously some output angular power distribution, we try to represent the mapping between them with the matrix operation, right? So the idea is that a given input direction is a particular row in this column vector, which means then the corresponding column in this transmission matrix is what you would get out if you put in a plane wave at that one input direction, right? So for different plane waves in different directions, you get different predicted outputs. Those go into the columns, and that's your sort of first cut at this matrix that maps the angular distribution on the input to the combined angular distribution on the output. And again, so in some sense, this is the piece that's capturing this fact that we're not just averaging overall orientations of the particle. And then we started asking ourselves, well, how do we think about multiple scattering in the plume? So if we think about the fraction that gets redirected after one mean free path, then we can write that down in terms of the phase functions. Again, phase functions, for those who don't speak aerosol, are basically like the differential cross section. They're related to how much goes off in the different directions. And then we have the single scattering albedo. Again, it captures how much of the extinction is caused by scattering as opposed to absorption. And then given that in a mean free path, we have by definition on average one interaction, then we can think about, we know that the probability of more interactions in a mean free path should be Poisson distributed. And so we think we can then sort of expand get the multi-interaction thing through sort of this Poisson structure here times powers of this single interaction matrix up here. And turns out you can write that as a matrix exponential. And so we call this M. And then we would expect that, well, maybe then if I want to go more than one mean free path, then I might think about modeling that as powers of this M matrix, as the transmission matrix between my input and my output. So that, again, first cut. And just to show you, this is for one of the micro club designs, some nominal parameters. This is what it looks like. So again, this is the phase function. So the way you read this is the illumination angle, okay, from 0 now to 360. Again, the convention that was developed by the people who did the full wave simulations is that 90 and 180 are the rotations that correspond to the two different directions along the main axis of the micro club. And then this is the output direction. So for a given input angle of illumination, then you read you get the particular range of different output values in the different output directions. And then using the definitions on the prior slide, we can write down this S matrix, which again is meant to capture a single interaction with one of these particles, and then the M matrix, which is meant to capture the Poisson distribution of potential different numbers of interactions in a mean free path. It's a little hard, they become, very diagonal, and it becomes hard to see. So we can go ahead and plot them on a log 10 scale, and so you can see that structure. And just to point out, the fact that this quadrant and this quadrant are different is the fact that scatter is asymmetric. If there was no absorption and reciprocity, then scatter, there was no extinction, was just the scatter, then the pattern that you would see here and the pattern that you see here would be the same. This matrix would be self-adjoint. It's equal to its transpose. And then this is the M, which again retains that difference in structure, but you can see it's muted in the M matrix. And then again, first cut, not meant to be a super rigorous theory, just trying to play with these ideas of what happens when we have these oriented structures and we're trying to propagate light through them. And so we can start to ask questions like, what happens? Can we evaluate how much of the light that comes out of the plume in the same direction it went in got redirected while it was in the plume and then put back on its axis? Because again, in the plume now we have a whole bunch of particles that are all oriented like this. It's possible that you can come in and scatter off one, but then in your interaction with another one be put back onto the original direction, okay? And because of the way the things are forward scattering and oriented because of the structure, that becomes more likely in this oriented plume than in a plume where the particles are randomly oriented. And so we can do things like we can create a version of S that only, that creates only the diagonal elements. So that would be what fraction interact with a particle and leave in exactly the same direction that they came in. And we can create a version of M, the multiple scattering version, that's built off just that diagonal version of S. And so that tells us how much went straight through, never deviating. And so if we look at the ratio that comes out in the original formulation versus the amount that comes through in this diagonal only formulation, we can start to look at what fraction comes out in the same direction it went in, but did this little jog inside and got redirected back onto the path. And then we can look at how that changes as we increase the number of mean free paths. And so this is the fraction that is non-redirected. This is how much of it didn't get diverted and rediverted while in the plume. When the plume is one mean free path, we're predicting that's essentially everything. But as the plume gets thicker and thicker and there's more likely to have been multiple scattering, we see that all of a sudden the fraction that was never redirected starts to drop. And so we start to have a significant fraction that gets deflected in the cloud, but then brought back to its original direction by another scattering event. But we can see also that there's this interesting structure where it still is like in the aligned directions, we're still, it doesn't decay as fast as it does in the directions which aren't aligned with the axis. Again, not sure exactly what to say about it, but we can start to ask and start to try to answer questions like this. And so after 10 mean free paths, it looks like somewhere, depending on what angle we're talking about, somewhere between 20 and 75% of the light was redirected while it was in the plume, but came back to the original direction. And so this suggests that multiple scattered light may contain useful image information. So it comes out, it was multiple scattered, but it's still coming out in the same direction it went in, and so may contain useful information that can be made use of. We can also start to think about contrast loss from interference. So again, when the scattering happens, some of the light goes off in other directions. But as we saw in the glare-based piece at the very beginning, the direction we're interested in is another direction for something over there, right? So when light from something over there scatters, it has a chance of scattering onto the path that we care about, the imaging path that we care about. And so we can start to put a limit on how much we might expect this glare, if you will, from other sources to impact us by what we started calling the white room model. Basically, we assume that all directions in space are equally bright, right? So the scene is white in all directions. And then we can look at the radiometric contrast of the desired piece direction we want to look, plus all the stuff that gets dumped onto our imaging path from sources in other directions. And we can see that when we're, again, one mean free path, relatively low amount of scattering in the plume, that contrast ratio is at least above 1. Okay, but as the plume starts to get thicker and thicker and optically thicker and thicker, then that contrast ratio starts to decrease. The thing we care about that we're trying to see gets swamped by light from all these other sources in the other directions. And so we would then conclude that probably trying to image through these plumes when we have significant bright fields is probably not going to be successful. And so this is one of the things that started to push us away from long wave into shorter and shorter wavelengths, because we want to not have everything in all directions. Out of these kinds of transmission matrices. And we just by looking at the structure of this M matrix, we can realize that the plume must have a complicated impact in imaging. So if this M was purely diagonal and had none of these other things, which are a little hard to see on this color map, here's the log 10, so you can see what's going on. If it was purely diagonal, then an input angle completely maps to an output angle. The value of that diagonal element tells us how much it got weighted, right? So that diagonal would be kind of like an MTF, right? Because we know angle maps sort of, to spatial frequency kind of information. Then if this was purely diagonal, then we would have an MTF-like behavior. Spatial frequencies would be weighted, and that would then be in the spatial domain a blur, right? If we have an MTF, then we have a PSF-like quantity. But we also see that there's structures in here that have this other directional shift. And so that's some circular toplets-like structure. And we know that a circular toplets-like structure is what we get from a convolution kernel. And so if it was purely circular toplets, then we would expect that it's like a convolution. So now it's TSF-like, and the spatial frequencies are blurred, but it's then a filter in the spatial domain. But of course, we have both. We see that there's these combinations. So it's more complicated than an optical element than either of these. So we're working to try and understand this impact. The other thing that's been a struggle for us is that, again, it's very computationally expensive for us to do these full wave simulations. This is angularly sampled way too coarsely to do any kind of true Fourier optics, Fourier imaging kind of analysis. So, we're trying to understand the best way to do that. Do we need to adaptively sample in the very finely along the optical axis? What's the best way to maximize our performance relative to a given computation time? Okay, so a lot of challenges in this in this problem. One of the performance challenges that I didn't bring up is we have not yet cracked how to break orientation symmetry. That is, we know how to use the acoustics to align the particles, but not how to orient them. We don't yet have a mechanism to make the scattering end always go in the same direction. We're looking at whether acoustic pulse sequences, like the kinds of things that are used in MRI, might allow us to whip the particle around in a meaningful way. Of course, we can always give the particle outriggers that don't have much optical impact, but do have strong acoustic impact, which would then allow us to potentially control how these things happen. And again, we don't have any rigorous way yet to how to connect these single particle properties to imaging performance in this in any kind of computationally efficient way, other than just doing that Monte Carlo rendering. So we're continuing to work on this transmission matrix approach and trying to think about this. But the thing that's been really fascinating to me is like, the problem statement that was given to us is interesting, but the thing that's been fascinating to me personally, just as a scholar, is the number of open questions that have sort of emerged and the kinds of things that the questions we're starting to ask, like, how does radiative transport work in an aligned aerosol? And again, Meredith this morning pointed me to some references she thought might have some insight into that. If so, I'm going to be super excited. But beyond radiative transport, how does imaging work in an aligned aerosol? And then, again, at some level, even the more exciting question is beyond the motivating application that was used to start this question. If you have the ability to align an aerosol, what is that good for? What are the things that you can use that for? And to me, that's a really interesting question to start pondering. Okay, so third approach to tackling vision asymmetry. So again, right now we can't break this orientation symmetry. We can't point this. We have reason to believe that the microclub would allow us to have stronger scattering in one direction, stronger absorption in the other, and that those would impact imaging performance, even if we can't quite say yet how, but we don't currently have the ability to do that, okay? And so one of the other techniques we developed was what we call temporally coded aligned particles. So this is the idea that I just spent a bunch of time talking to you about. The idea is that they're oriented, they're aligned and oriented. We get this fundamental asymmetry. It requires this ability to do this, which we can't do right now. Okay, and then the idea is maybe we get this trade-off between absorption, that we can maybe we lose SNR, but maybe we can build it back, or at least we can apply gain or other image retrieval kinds of things. Whereas in the other direction, we get a higher SNR, but it's been scrambled. But what we can do is we can align. We can't align and orient, but we can align. So what if we temporally vary the alignment in a coded pattern that we know and the other side doesn't? And so the idea is not to create a fundamental asymmetry, but to create an effective asymmetry in the availability of image information. So the idea is the side that we want to have better ability to see only collects photons in the windows when the particles are
aligned in a way that reduces the extinction. Okay, and so we get better imaging in these momentary windows when the particle is aligned. We know when that is, so we can accumulate photons in those windows, whereas somebody who doesn't know the code pattern is accumulating photons all the time, including when the scatter is very high, when the extinction is large. Okay, let me back up. So I'm going to show you an experiment. So we have a water chamber where we've started to play with this idea and just, the basic idea of, can you see better through an aligned plume of particles? So the video that's going to come up, hopefully it's bright enough, is a fluid chamber. It's got the microclubs in it, which are not necessarily the ideal particle for this approach. And about 3 seconds after I switch the slide, the ultrasound is going to turn on in the chamber. Okay. So right about now. Again, contrast a little bit low on the screen, a little bit better on mine, but there is clear visibility improvement when the particles are aligned than when they were unaligned. Again, it's the microclubs. It's not the ideal particle for this. The orthogonal view, which you don't have an image of. So first of all, the particles are aligned on an axis going into the screen. The orthogonal views remain murky throughout the entire experiment that you see the video of. When we turn up the acoustic amplitude, we can see the effectively wind in the liquid. We can see the particles stream to one side. We can also see standing waves form, because again, it's very hard to kill the reflections, and we see the particles cluster, but we don't see them at this lower intensity. We believe that this is actually the visibility improving as the extinction changes as we orient all of the particles in the solution. Now they do settle over time. We would love to have some better improvements. We'd love to have sort of multiple views. Simultaneously, we'd like to have a clear indicator of when the acoustic field comes on. We'd like to do this at multiple low amplitudes. So the one thing I didn't talk about is the time scale of the rotation is dependent on the acoustic power. And so if we did it at a variety of acoustic levels, clearly, then, and we saw different time scales of clearing, that would be the sort of definitive experiment. So we're working on building a new chamber design to facilitate these goals.
What is the time scale on that sort of like settling?
Oh, it's way longer than this video.
But are we talking like 10 seconds or like minutes?
Probably tens of seconds in the fluid. Maybe even a few minutes, I think. So we've had, with this temporal coding version, we had good success. We were able to meet those program goals, the PD and PID metric goals. Their ratio was the thing. I can't show you the results because I wasn't allowed to see the results. I just know that we actually hit the goals that were achieved, which specifically was that we were able to get a specific value of PID greater than being PD, and there was a specific ratio that had to be achieved when PD was 0.5. And again, this was done with a particle that had been completely unoptimized for this new approach. So there's a lot that can be done on this axis. So again, we were using the microclub copper nanowire. Our simulations seem to indicate should be significantly better. We can actually go a little bit longer because we're no longer trying to make this asymmetry between scatter and absorption. So we can make the wire a little bit longer. Synthesis and everything becomes a little bit simpler. And it turns out that we want to explore actually what the two alignment states are. Basically, aligned and orthogonal probably aren't the two best options because the aligned is so good that too much information leaks through and it doesn't get degraded enough by the orthogonal. And so optimizing the pair of states, so maybe it's orthogonal and 30 degrees or something like that is an optimization parameter that still has to be explored. All right, just last thing, what's next? So ongoing work, I mentioned we're working to build an updated water chamber. So here you can see the central water chamber. This is just water at this point, but where the particles would go. We have the acoustic transducers. These chambers on the other end are transparent so that we can get sort of semi-orthogonal views kind of through here without running into the transducer. And they contain transparent goo that's really good at absorbing acoustic energy to try and minimize the reflections from the impedance mismatches back into this chamber. We've also started building, here you see a CAD rendering, I don't have a photograph, started building a tabletop air chamber where we can do some initial experiments. We've got an IR target projector that we can use. We also have a mid-wave laser that we can put through a chamber that has acoustic inputs to align the particles. They would be aligned. So with these two acoustic inputs, the particles will be aligned in an axis orthogonal to this face here. So they'd be aligned that way. And then that whole chamber is on a rotation stage, so we can explore deviations relative to the axis of the aligned particles, either again with a target projector if we want to do scene type experiments, or with a mid-wave laser if we want to do radiometric or some type of quantitative scattering measurement. And with that, 3 minutes, so I think I've used my time. Thank you so much for your time and your attention. I really appreciate it.
Yeah, 3 minutes. This means we have time for 1.5 questions. Masoud.
Compass needle is light enough to easily be aligned in the magnetic field of the Earth.
Say that again?
A compass needle is light enough to align itself with the magnetic field of the Earth. Some of these anisotropic particles of yours, which are magnetic, would they use the magnetic field?
That's an interesting idea. To be honest, I hadn't thought about that. There was another team on this project has some similar ideas, and they've been discussing using electromagnetic fields, primarily electric fields. And of course, the drawback is that becomes completely infeasible at standoff. But the idea of using the natural magnetic field, I think, is a really interesting antimagnetic material. I think that's a fascinating thing.
So you say the electric fields are infeasible in standoff. I guess I don't understand how that would be any different for something like an acoustic wave. If you still have to do some sort of collimation with the acoustic wave.
I do, but you need in order to rotate these things, you need many kilovolts per meter. So you basically cross the spark threshold for electric fields for gaps bigger than millimeters. So like they were able to do experiments on like microscope stages and stuff like that. But I don't how you have something you can make a propagating electromagnetic field. But the power densities you would need would be you'd be focused, as opposed to with these ultrasound ones, we can make patches, we believe, many meters across at the required density. So if you were trying to do static electric fields, of course you need the ability to put electrodes out there and you start to make big sparks.
Any other questions?
How does the degree of coherence of the light play in this? Can I just send a laser like asymmetrically?
Yeah, so that's an interesting question. We have been looking primarily assuming spectrally broadband not over hundreds of nanometers, but at least over a relatively broadband. I don't know. I mean, the short answer is that's not something that we've thought carefully about because we don't even know how to do sort of incoherent radiative transport through this aligned structure in a way yet. But it is a very interesting question. I agree.
Last question.
Thank you for the talk. On your slide where you showed the creation of the copper-2 nitrate precipitate.
Yeah.
Can you tell us more about the, I guess, choice in those particles? Or I'm just curious what other properties you were going for. Just pointing out obviously the
Yeah,
paramagnetic, yeah.
yeah, so let's, so, kind of here. So really, this is sort of all we had started to consider. So like, again, this is a huge parameter space that has not been explored at all. So it was very much, what did we know how to create that could put these, dielectric, conductor structures together in a very easy, natural way. What would give us rod-like structures that we could align. And well, I guess those two things, because this one is the one that meant that we thought we would get the scatter and absorption. So how much thought has been put into it? Almost none. Like in the sense that like this met these things. And I think you could you could spend an entire research project just trying to answer the question that you asked, right?
Yeah.
Yeah.
Okay, so let's thank the speaker again.